Hey everybody, here's another projectile motion problem for you. This one might be a little bit more challenging. I'd encourage you as you're watching this to try working out the problem yourself, and then when you get to a point where you're stuck, go ahead and continue watching the video. But don't just watch it through, see what you can do with this one on your own as well. So here we have a baseball situation. This one's a little bit different because we have the initial velocity's direction, but not the magnitude of that. And that's what we're looking for on this one. So that'll change how we set things up just a little bit. But we always begin with a picture and with a list of variables that we know. So let's start there. So we're looking at something like this, where we've got some horizontal distance known there. We have our vertical distances or vertical positions known as well. We know a little bit about the starting situation, but not very much, pretty much nothing about the ending situation. This is definitely a problem where when you first look through it, it's going to look like we just don't have enough information to solve it. But I promise we do. Stick with me. Let's do the given information next. For our positions, we might as well say that it starts at a position of 0 and ends then at 110 meters for the horizontal direction. For the vertical direction, we could certainly say that it starts at a position of 1 meter and ends at 3, but it's nice to have zeros in there to have terms drop out. It probably doesn't matter too much on this one, but I'm going to go ahead and say that it starts at 0 and ends at 2 meters instead, 2 meters above where it started. You get to choose your coordinate system, so might as well choose it so we simplify our math just a little bit here. As I said, though, not a big effect on this one. Acceleration we always know, 0 for the x, negative 9.8 meters per second squared for the y, and we have that 30 degrees, but we really don't have a home for that right now. I'll tell you what we'll do, though. Let's go ahead and draw out this initial velocity vector with its x part and its y part. We know that's 30 degrees, and we know that this is Vx naught and Vy naught. And even though we don't have values to put in there, let's go ahead and write an expression for Vx naught and for Vy naught, because that's going to end up being useful here. In general, when it looks like you don't have enough information to solve, the two things you'll want to do is go back to the problem and see if you missed something in the given statement, and if not, then just start writing all the relationships that you can find and see if maybe a couple of those relationships can be combined. We call that solving a system of equations, and you'll need to do it more often than you might think. So we'll go ahead and write an expression for Vx naught and Vy naught. Here Vx naught is going to be V naught times the cosine of 30 degrees, and Vy naught is going to be V naught times the sine of 30 degrees. And we could get decimal values in there as well, and when we do that, since the cosine of 30 degrees is 0.866, I'll just go ahead and write this as 0.866 V naught. And the sine of 30 degrees is a half, so I'll put that as 0.5 V naught. Now, effectively what we've done here is reduced the number of unknowns we have. We still don't know Vx naught and Vy naught, but we've rearranged things so that it appears as though there's only one variable, V naught, that we don't know between those two. Since we have the starting velocity in the x, we also know the ending velocity in the x. Now we're going to have to do more than just write these in terms of V naught. We need numbers eventually, but this would be a good first step to get there. So now let's start taking a look at the equations. Let's just start with a preliminary investigation into each of these equations and how useful they might be. So in red I have the x versions of the equations, and in blue I have the y versions, just so we can keep those straight. Starting in the x with this first equation, when I plug in the numbers that I have here, for Vx and Vx naught, I'm going to have this same expression, and then acceleration is 0, so 0 times time is just going to be 0, so this one would end up with this 0.86 V naught equals 0.866 V naught. or 1 equals 1, which is one of those true but not useful statements. So I'm just going to cross that out as one that I'm not going to be able to use here. The other two I could look at as well here. Let's actually skip down to the third one for just a minute. We have kind of the same issue there. We have this acceleration term in it, and since acceleration in the x is 0, I forgot to mark down that that was acceleration in the x, but acceleration in the x is 0, that's going to mean that this whole term drops out, and I'll just have that 0.866 v naught squared equals 0.866 v naught squared. So again, not a useful one. Now, if you haven't noticed the pattern, every time we do these problems, since acceleration in the x is always 0, and having acceleration in the x equals 0 means this equation and this one are useless, this second equation is the only one we're ever going to do anything with in the x direction, unless we have some acceleration in the x direction. Now in the y direction, all three of these could be useful. So let's take a look at this equation then. I have a number for x and a number for x naught. I don't have one for the initial velocity in the x or for time. Over here, well, this whole term is just going to drop out. So this expression then is going to be left over. Just mark that part. Just this part, because this will go to 0. And so I find that this expression allows me to figure out Vx naught in terms of t. Well, that's a good start, and since I already have a relationship between Vx naught and the overall V naught that I'm looking for, that's a great way to go. So let's see what we can do on the y side about finding out what t would be. So looking over on the y side, I've got this first equation has t in it. And in order to figure out t, I would need to know acceleration in the y, which I have, initial velocity in the y. Oh, I sort of have that. Not really, though. I just have the expression for it. And final velocity for the y, I don't have that one. So I'm just going to go ahead and mark that that's not going to be a useful equation for us. When I look down at the third equation, there's no t in that equation, so I can't use that to solve for t either. So it looks like I'm using the same equation in the y direction that I did in the x direction. Now, when I look at this equation in the y direction, y and y naught are both known to me again. Vy naught is unknown. T is unknown as well. So I'm not going to be able to use just this equation to solve for time. I have two unknowns in that equation. Now, the unknowns here are the Vy naught and time. Over here it was Vx naught and time. But since I have these expressions for Vy naught and Vx naught in terms just of the original or the overall initial velocity, I can plug those in, and then I have two equations with the same two unknown quantities. And from there, we can solve. We can solve this as a system of equations. So that's our path. I'm going to go ahead and write out these two equations with everything I know in them, and then we'll substitute in those expressions up here for the components of the initial velocity. I am kind of breaking my own rule here about not putting in numbers until I'm done with the algebra. When I get to these situations where I have multiple variables that I'm trying to figure out, I find it useful to have numbers in for everything that I know. That way I don't get confused on what it is that I'm trying to solve for. Now in red we have the x equation, in blue we have the y equation. We still don't have a common variable though. We have three variables between those two equations. This one, and then time. So we need to put those all in terms of just the overall initial velocity, and then we use that to solve for the overall initial velocity. So on the x side, I'm going to put in this expression. On the y side, I'll put in this expression. And now I've got two equations with the same two unknown variables, and so I can solve for these. Now, there's always multiple methods for solving for systems of equations. Here, I think probably the easiest way is to solve by substitution. I could use these to solve for either t or v naught, but since it doesn't ask me to solve for or for the time rather, I'll go ahead and just solve for v naught. Now to do that, I'm going to rearrange one of these equations so that it reads t equals, and then some expression with v naught in it, and then plug it into the other equation in place of the t's. So those t's will drop out completely, and then we'll have an equation just with v naught in it. Looks like this one's the easiest one to rearrange, so I'm going to go ahead and rearrange that one in terms of the to get t on a side all by itself. So the 0.866 v naught t, I'm just going to go ahead and divide both sides by 0.866 v naught, 0.866 v naught, and I'll just calculate the value for 110 over 0.866, and so that gives me 127 meters over v naught is equal to t. And then I can take that and put it into this equation every time I see a t. Now this is by no means an easy equation to work with. It is a little bit ugly, but it's a solvable equation. So that's what makes it a challenge problem here, that we have to do the extra algebra stuff. The physics isn't any different from what we've done though. So let's go ahead and plug in this expression every time we have a t. And to make it clear, I put the substituted part in red. I also am just going to go ahead and drop the units for right now, just because I think they might get in my way, and I might confuse those with a variable that I have to solve for. Your units are a great tool for making sure you do the algebra right, but if you recognize that they're just going to screw you up, then definitely drop them. Don't include them if they're going to be more help than they're worth. Do go through and check that the units make sense before you finish your answer, though. So on this one, I see that I've got the v naught here and a v naught here, and those are going to cancel. And then I'm left over here with a v naught squared in the denominator. So I'm going to have to take care of that. But let's go ahead and see what we get so far. So we have 2 over here. The 0.5 times 127 is 63.5. And there's no v naughts there. And then minus the 127 squared times the 4.9 is equal to 79,032 divided by v naught squared. Next step in the algebra, we generally leave the terms that have v naught in them where they are, and then move everything else over to the other side first. I'm going to do that here too, so I'll subtract the 63.5 from both sides, and I get a negative 61.5 is equal to negative 79,032 divided by v naught squared. Now I can't solve for that v naught squared when it's in the denominator, so I'm going to go ahead and multiply both sides by v naught squared, and I get negative 61.5 v naught squared is equal to negative 79,032. At this point, this ought to look like a more familiar problem, something that you're more used to solving. So I'll divide both sides by 61.5, and when I do that, I get v naught squared is left over here. V naught squared is equal to 1,285, and then I'll square root both sides, and I get v naught is equal to 35.8. And then that's a velocity, that'll be meters per second. And that's our minimum speed. Since the question asks for minimum speed, not minimum velocity, we don't need to include a direction there. But if they asked for minimum velocity, the direction would be at 30 degrees. They already told us that, 30 degrees above horizontal here. Alright, lots of algebra there, solving a system of equations, so some extra math stuff, but the physics stuff hasn't changed at all there. Keep in mind that that idea that when it doesn't look like you have enough information to solve for something, just find all the relationships that you can, and we'll see if we can make something happen with those relationships. See what we can combine or what we can solve as a system. But that's all for now. Let me know if you have questions. Be sure to comment in the comment on this. Add it to your favorites. Subscribe to the channel. Whatever you want to do with that stuff. But please do let me know if you have questions.